Okay, let's get our feet underneath us as far as doing some probability problems. Okay, I'm going to do some fun problems with complements with you guys, just to give you another skill sort of in your toolbox. So let's talk about complements first and foremost. Complements. All right, and hopefully you recall that the probability of an event plus the probability of that event's complement is equal to 1. Well, real simple algebra tells me that I can write the probability of the event as being 1 minus the probability of its complement. Now, let's do a problem that uses complements really, really nicely, because otherwise things can get out of hand. Let's say that we're going to flip a coin 5 times. And I want to figure out the probability of at least one head. Now, as soon as I see this right here, this little notation right there, my spidey sense starts to tingle. And I'll explain why in just a sec. Now, I'm going to change the color of pens so that hopefully I can indelibly mark something in your souls. The problem with this is, if you think about it, is how many ways are there? Remember, we got 5. Flipping a coin 5 times is exactly the same thing as flipping 5 coins all at once. So what we would have to think about if I wanted to figure out the number of ways to do at least one head is the probability of exactly one head, or, because they can't happen simultaneously, the probability of exactly 2 heads, or et cetera, all the way up to the probability of exactly 5 heads. In other words, you flip the coins and all 5 of them are heads. So I would have to figure out each one of these individually, and believe it or not, that's going to require a little bit more mathematical savvy on our part. I should probably write an or in there. All right, but because I am so clever, let me go back to my black pen, which indicates cleverness. What is the complement of at least one? At least one. Oh, it's none. The complement of at least one is none. So think about that. Wouldn't the probability of rolling at least one head be equal to, because of this property right here, 1 minus the probability of rolling no heads? Think about that for a second. 1 minus the probability. Well, what's the probability of rolling a not head on a coin? Rolling, let's try that again. Flipping a not head. How many times have I said that? Flipping a not head is just the half, right? Because that's the probability of flipping a tail, which is the complement of a head. There's no other thing, there's nothing else to flip on a coin. So the probability of flipping no heads out of 5 coins is 1 minus, well, excuse me, the probability of flipping no heads is flipping a tail on the first, flipping a tail on the second, flipping a tail on the third, flipping a tail on the fourth, and flipping a tail on the fifth. These are all the probabilities of flipping heads, or flipping tails, excuse me, which is the complement of a not head. So if I want to know the probability of at least one head, I simply go 1 minus its complement, and that's what this is. So what is that? 1 minus 1/32th, and I get 31 out of 32. So the experimental probability, the theoretical probability of getting at least one head out of 5 coins is 31 out of 32. That's a wonderful tool, but the thing that you really have to pay attention to here is your spidey sense, your bunny ears better perk up when you hear at least one, because the complement of at least one is none, or in this case, no heads. All right? So let's do one more, just for giggles. Let's play Yahtzee. Nah, we'll play Yahtzee, but we'll play liar's dice. We'll play Yahtzee with, I don't know, let's roll 10. And you can try this one on your own. Roll 10 die. That's a lot of die. Roll 10 dice. Okay? And I want to know the probability of getting at least 1 4. Oh, look at that. Ding, ding, ding. Bells and whistles. Try it. Just try it for a sec. Pause the video and see if you can figure it out. Okay. Hopefully you paused the video. You should have done it, but maybe you didn't. This is 1 minus the probability of getting no 4s. All right. Well, what's the probability of getting no 4s? So let's give ourselves a little room. Probability of getting no 4s. Well, okay, wait, we got to ask ourselves, are these independent? Yeah, rolling die is independent. In other words, the outcome on one die, it doesn't affect the outcome on another die. So let's say I've done this 10 times. So a not 4, there are 5 ways to roll a not 4 out of 6 sides. So that's going to be 5 out of 6. There are 5 ways to not roll a 4 out of 6. And because they're independent, I'm going to multiply, and I'm going to do that 10 times. So it's 5 6 to the 10th, and it's 1 minus that. All right, now I would need a calculator to figure out exactly what that is, and I just happen to have a handy-dandy calculator. Hopefully you're patient with me, so I'm going to go 1 minus paren. I hope I don't overload it. I shouldn't. 5 divided by 6 and paren 2 to the 10th, and I get point. This is equal to 0.838, or approximately equal to 83.8%. This is approximate, by the way. Okay? Pretty cool, huh? Complements are super powerful, but be careful because you got that at least one that's the key phrase that you're looking for. All right? I'm going to go ahead and I'm going to build a chart, and we're going to play around with some dependent probabilities here in just a sec. I'm going to build a chart and build a Venn diagram that we can play with. So I hope you enjoyed that, and I'll see you back in just a second. All right, so what we're going to talk about now is called conditional or dependent probabilities. It's usually referred to as conditional probability, and it comes from that same formula that we talked about before. All right, so I know that the probability of A and B, if it's dependent, is probability of A times the probability of B given A. But in a puff of algebra, you can write this as the probability of B given A is equal to the probability of A and B divided by the probability of A. All right, so you see how it's the same thing? Now, we're going to play around with this just a little bit, excuse me, with these two charts that I just did. So let's have a little bit of fun. All right, now, first things first, if I'm looking at this Venn diagram and I eyeball this thing, hopefully it's relatively easy to see that what n equals 70. So if I'm looking for the probability of a math student, all right, the overall probability of a math student, excuse me, what I'm doing is I'm simply looking at the number of math students, which it appears to be 20 plus 5, because remember this 5, hopefully you've seen a Venn diagram before, but this 5 represents the students that are taking both math and English. These are the students that are taking math exclusively, and these are the students that are taking English exclusively, excuse me. So the probability of math, in this case, is the total number of students that are taking math divided by 70, right, which is what, 5/14? However, watch this. Now, I'm going to show you two ways to do this. There's a real intuitive way to do this, and then we're going to use the formula. Now, let's go ahead and go through this, and I'll show you what I mean. I'm going to do the probability of math given English. All right? So in other words, what's the probability of finding a student who is taking mathematics given that they are taking English? All right? Now, watch close. What that says is, because this says given English, that means that our sample space has been reduced down to this set, because this is the set of given English. So watch how it works. What is the probability of finding a math student given that they are taking English? Well, it works exactly the same way. All I'm going to do is I'm going to count the number of math students, which is 5. Those are the students that are taking both math and English. And I'm going to divide it by the total number of students that are taking English, which is 5 out of 50, which is affectionately known as 1/10. Now, watch this. I'm going to use the formula, okay? So the formula says what's the probability that a student is taking both, or excuse me, math given English, so the probability B given A, is the probability of a student taking both math and English in the numerator, which is 5 out of 50, divided by the probability of A, okay, which in this case is B given A, math given English. So the probability of English is 50 out of, wait, did I do 5 out of 50? I'm sorry, I meant to do 5 out of 70. let's back that train up. This is 5, whoa, we got a lag here, bear with me, 5/70ths divided by 50/70ths. Now, let's go over this one more time. Notice that there are no givens in this formula. It simply says find the probability that a student is taking both math and English, or A and B in this case, which is 5/70, and I divide that by the probability of English. Well, that's 50/70. My 70s cancel, and I end up with 1/10 yet again. Isn't that cool? I can simply use my formula, no problem. All right, I hope you guys are starting to figure out that every time I see data, or I see a chart or anything like this, the first thing I'm going to do is I'm going to find some totals, because my brain just works that way. So first things first, I'm going to total up these these rows. This is 22, this is 18, this is 27, and this is 13. And you notice that in both cases this sums to 40, which is equal to my m. Now let me explain this just a little bit. Let's say that you go out and ask a bunch of people what was their favorite movie last summer. Was it Harry Potter or Twilight? I think Twilight came out last summer, but who cares, right? All right, now let's play with a few probabilities. All right, I know that my sample size is n. What is the probability that I asked a male? All right, well, all right, so I find the total of males, which is 22, and I divide it by 40, and I get what, 11/20ths. All right, about 55%. What's the probability of finding somebody that liked Twilight? Well, again, I just go 13, and I divide it by 40, and I'm done. Easy peasy. All right, now let's find the probability that somebody favored Harry Potter given that they were female. Watch how this works out. Given that they were female. Now, there's two ways to do this. I can strictly follow this formula over here. No problem. We'll go through that here in just a sec. I'll do a couple of these just so you can wrap your brain around it. Or you can do it intuitively. What this says is, check it out. If it says given that it's female, it means that our sample space has been reduced to just the set of females. All right? Because it's given that it's female. In other words, once we say that given that it's female, just like over here, it was given that it was English, we ignored the math part that wasn't English. The same thing over here. Given female. Well, look at this. Probability that they liked Harry Potter or preferred Harry Potter, given that they're female, is the number of females that liked Harry Potter, which is 12 out of 18. It's actually known as what, 2/3? Now, let's use the formula. All right? Now, I'm actually going to write this out. This is going to be the probability of Harry Potter and female, and female divided by the probability of female. And watch how the numbers work out. Again, we'll do this one more time. All right, so the probability of Harry Potter and female, let's look. That's Harry Potter and female. That represents this cell right here. So that's 12 out of a total of 40. That's the probability that you grab somebody and they are both female and preferred Harry Potter. The probability of a female is there are 18 women, right, out of a total of 40. So I got 18/40ths, and look at this, same thing. Isn't that right? That's so cool. I love that. All right, now let's flip it around. Let's find the probability of, let's go, a male, given that they liked Twilight, that they preferred Twilight. All right, now the jokes write themselves, but you can play around with that. All right, now look at this. Now what this does is it reduces, remember, it reduces our sample space, given that it's Twilight. So anything not Twilight doesn't even matter anymore. We can throw it out, okay? So there's a total of 13, 13 Twilight prefers, or whatever you want to say, and there are 7 males that did that. So just by looking at it, I can go 7/13. However, if I use the formula, it's the probability of male and Twilight. That represents this cell right there. So 7 out of 40 divided by, I'm going to run into the margins again, sorry about that, divided by the probability of Twilight, which is 13 out of 40. And whoa, 7/13. That's awesome, isn't it? A little over half. So cool, all right? That's called conditional probability. It looks intimidating and the formula looks a little crazy, but hopefully this example helped you out a little bit. All right? Cool.